Watson 2.0 is a robust model for question asking and answering given an input of some text. The first part of this model is question asking, which goes through the text creating questions based on each viable sentence. Before creating our current question asking model, we attempted to write handwritten question templates, which we soon realized was too extensive a task to complete. We then tried using stanzas grammatical tagging and lemmatization to ask questions about who did the next verb in the sentence, but this led to short, often unanswerable questions. Our current model is more effective at creating good questions and uses dependency parsing from stanza to ask who, what, and why questions by rearranging the clauses within sentences. The model creates who and what questions by finding the sentence root, choosing between who and what, depending on the type of named entity noun subject whose head is the root, and identifying and adding the verb phrase starting at either the main verb or at the auxiliary or copula preceding it. The model can also create why questions by looking for sentences including instances of because or due to that suggest causation. The algorithm finds the word serving as clause head of because or due to, and then finds the head of that word, which will center the effect that the question will ask about. Once located, our model deconstructs the components of the effect clause: the noun phrase, the verb or auxiliary, and the verb phrase. If there is an auxiliary in the sentence, it is added after the why in the question, while the question verb becomes whatever follows the auxiliary. Otherwise, did or does is added after why based on the tense of the main verb, and the lemma of the main verb becomes the question verb. The noun subject is then added between the auxiliary and verb in that question. After appending the rest of the verb clause, excluding the explanation, the question is then returned. In addition to our question asking system, we originally intended to include a grammar parser to test if our questions were grammatically correct. The parser would have been implemented by using the spacey part of speech tagger to tag the sentence and check if the sentence was grammatically correct according to the CKY algorithm described in class. Unfortunately, inaccuracies in the part of speech tagger meant that the parser would label some correct sentences as incorrect, and because our final question asking system was consistently accurate, the CKY parser was not included in the final working system. Watson 2.0 also has a question answering model. We decided to use BERT to extract sections of the text that could contain question answers, and then use additional processing to extract the exact answer from that section of text. We thought using BERT would be the best way to obtain the correct section of text because it is good at creating semantically based vector embeddings for sentences, is pre-trained and thus fairly fast, and had been taught in class. We chose to use Sentence Transformers, a library that has a pre-trained sentence BERT model, because we are trying to match the entire question, a sentence, rather than specific words within it. Once we create BERT embeddings for the question and every sentence in the text, we compare vector embeddings using cosine similarity to find the sentence most similar to the question. At first, we tried to rely solely on the BERT embeddings by returning the highest scoring sentence, but we quickly found that there were often several sentences with very similar scores since the entire text is based on one topic. To improve on this method, we implemented a simple bag of words model to choose between the 5 highest scoring sentences by counting the amount of identical words in the question and each sentence. The sentence with the most identical words, its corresponding similarity score, and the question are then input to a function which extracts the answer portion of the sentence. We use 3 separate approaches based on question type: one for true, false, or yes/no questions, one for why questions, and one for the rest. We categorize a question as true/false if it contains true, false, truth, or fact in any of its lemmas. We categorize a question to be the yes/no type if be, will, can, would, have, could, do, yes, or no appear as the first lemma in the question. For the yes, no, and true-false questions, we set a threshold of 0.000137 for BERT similarity scores, a number decided by extensive testing. We found that true yes answers tended to be above this score, while false no answers tended to be below. For questions which start with why, we look for because or due to in the answer, because the sentence portion after these indicators tends to be relevant to the answer. For all other questions, we rely primarily on dependency parsing to extract the precise answer phrase. Our first step is to find the theme of the question by identifying either the question root, when the root is a verb or auxiliary, or in the absence of such a root, the copula linking the subject to the predicate. We then find all matching lemmas in the answer sentence. We treat each child of each of these lemmas as a potential answer head. We remove answer heads, which also appear in the question, to prevent answering with a portion of the question itself. Then, to build answer phrases, we find all of the children of each head and combine them into a phrase, making sure to include full NER phrases. Once we have potential answer phrases, we deal with the individual special cases of who and when questions. For questions which begin with who, we create a list of all the answer phrases containing NERs referred to as who. For when questions, we create a list of all answer phrases which contain a date, time, or event. These lists become the new potential answer phrase list as long as they contain at least one entry. Having established our final potential answer list, we return the shortest answer phrase unless there are no phrases in the list, in which case we return the topic of the article as a strategic default answer. We did this for conciseness and because we found through testing that the shortest answer tended to be better than the longer ones. Thank you.